In our lecture on chirality and enantiomers, we have seen that flask and its mirror image are superimposable. We called such objects as achiral. Another way of checking the chirality of the objects is to see if the molecule has a mirror plane of symmetry. As we can see, the flask has a plane of symmetry, which bisects the object in such a way that the two halves are mirror images of each other. Such objects are said to be achiral. Likewise, we have seen that the mirror image of a left hand is the right hand, and the two are non-superimposable. We called such objects chiral. Such objects don't possess the plane of symmetry, whichever way we try. These objects, that can't be bisected by a plane into equal mirror image halves, are said to be chiral. Same applies to molecules also. Achiral molecules are superimposable on their mirror images, which indicate that the mirror image is the same compound. Consider this molecule, designated as C. Its mirror image looks like this, and is designated as D. If we try to superimpose D on C, it appears that the two are not superimposable. However, if we tip C on its side, the new representation of C looks like this. Now, this new C can be seen fully superimposable on mirror image D. Such a molecule is said to be achiral. Just like we did in case of flask, another way of checking if this molecule is chiral or not is to check if it has a plane of symmetry. For this, let us look at this molecule from this side. The green and blue groups face towards the observer, and the black ones seem to be away from the observer. So we draw the flying wedge of this molecule like this, with green and blue groups on wedges, and black ones on dashes. If we draw the plane passing through the bonds connecting blue sphere, carbon, green sphere, we see this plane divides the molecule into two equal halves, which are mirror images to each other. Thus, this molecule is achiral, as it has a plane of symmetry. Because any structure with a plane of symmetry cannot exist as two enantiomers. Consider this molecule, called chlorofluoromethane. This doesn't have a chiral center, and hence we know it is achiral. Let us check if it has plane of symmetry or not. The corresponding ball and stick model of this molecule can be shown like this. This is fluorine, chlorine, and these are two hydrogens attached to carbon. Look at this molecule through fluorine-carbon bond. If we rotate this molecule by 90 degrees, so that fluorine and chlorine go backwards, and two hydrogens come forward towards the observer. Then pass a plane through fluorine-carbon-chlorine like this, we see it divides the molecule into two equal halves, which appear to be mirror images of each other. The corresponding flying wedge representation of this molecule can be written like this, with two hydrogens on wedges, fluorine and chlorine on dashes. As in ball and stick model, we can pass the plane through bonds connecting fluorine-carbon-chlorine. This plane divides the molecule into two equal halves. In both flying wedge and ball stick model, we can see that part on left side is mirror image to the part on right side. Thus, this molecule has plane of symmetry and is therefore achiral. Therefore, molecules with plane of symmetry are achiral as they can't have enantiomers. Consider another molecule, bromochlorofluoromethane. Since four different groups are attached to carbon center, this is asymmetric carbon. From our lecture on chirality and enantiomers, we know that asymmetric carbon is a type of chiral center. And any molecule with just one chiral center is chiral overall. The ball and stick model of this molecule can be shown like this. If we look through fluorine-carbon bond and rotate the molecule by 90 degrees in this manner, so that fluorine and chlorine go backwards and bromine and hydrogen comes forward, towards the observer. Then pass a plane through fluorine-carbon-chlorine like this, it doesn't divide the molecule into equal mirror image halves. The corresponding flying wedge representation can be written like this, with hydrogen and bromine on wedges and fluorine-chlorine on dashes. The plane passing through fluorine-carbon-chlorine is shown in red dashes. In both representations it can be seen that left side part is not the same as the right side part. Thus, this vertical plane is not plane of symmetry for this molecule. Likewise, if we draw a horizontal plane passing through bromine-carbon-hydrogen, it also doesn't divide the molecule into two equal mirror image halves. The corresponding flying wedge representation can be shown like this. The plane passing through bromine-carbon-hydrogen is shown in red dotted line. It is clear that, across this plane, the top part of the molecule is different from the bottom part. Thus, these are not the plane of symmetry. This means that the molecule doesn't have plane that can divide it into mirror image halves. Thus, if a molecule contains one carbon atom carrying four different groups, it will not have a plane of symmetry and must therefore be chiral. That means, if a molecule contains one chiral center, then it will not have a plane of symmetry. However, the presence of chiral centers doesn't guarantee that a molecule is chiral. Take for example, cis-1,2-dichlorocyclopropane. It can be drawn either with both chlorines on wedges or both on dashes. This molecule has obviously two chiral centers marked with star. If we draw a plane through these molecules like this, which passes through carbon-3 and midway between carbon-1 and 2, we can see it divides the molecule into two exact mirror image halves. Thus, this molecule has plane of symmetry and is therefore achiral, despite having two chiral centers in the molecule. Now consider trans-1,2-dichlorocyclopropane. Trans means that one chlorine is to be placed on wedge and one on dashes. This molecule also has two chiral centers, both marked with star. If we draw a plane passing through carbon-2 that passes midway between carbon-1 and 3, we can see that it doesn't divide this molecule into two equal mirror image halves. Likewise, if we draw a plane passing through carbon-1 that passes midway between carbon-2 and 3, we can see that it too doesn't divide the molecule into two equal mirror image halves. Similarly, if we draw a plane passing through carbon-3 that passes midway between carbon-1 and 2, it also doesn't have two equal halves across the plane. This half has chlorine on wedge, whereas this half has chlorine on dashes. Thus, all these lines don't represent plane of symmetry. Therefore, this molecule is chiral because it has two chiral centers and no plane of symmetry. A molecule is called meso if it has at least two chiral centers but has a plane of symmetry that makes it achiral overall. Consider this molecule, cis-1,2-difluorocyclohexane. It has two chiral centers marked with star. If we draw a plane like this, we can see it divides the molecule into two equal halves. The right half appears exactly as mirror image to left half. This means the molecule has a plane of symmetry. Thus, the molecule has two chiral centers, but has a plane of symmetry is present, which makes the molecule as meso and achiral. If we now consider trans-1,2-difluorocyclohexane, it also has two chiral centers. but trans means the two fluorogroups are pointing in opposite directions. If we draw a plane which passes through all the carbons of the ring, we can see that across this plane, one fluorine points upward and one downward but at different carbons. This means these are not the mirror images of each other. Similarly, if draw a vertical plane midway between two carbons holding fluorines, we can see the two halves across this plane are not equal. Thus, this molecule has two chiral centers but a plane of symmetry is absent in this molecule. Hence it is chiral overall.